So in this lecture now we'll state and prove the under certain condition the solution of Cauchy's problem for nonlinear PDE is exist and it is unique. So as we have solving in my previous lecture a solution of a Cauchy problem for nonlinear differential equation, we'll consider this partial differential equation of the form f of x, y, z pq equal to 0, and I will call that equation as 1, where this function f is the second order partial different function is whose second order derivatives are exist with respect to x, y, z, p and q, with the condition that fp or fq, both of them, either of them is non-zero. Suppose there is an initial curve is given to us. That initial curve we have denoted as gamma 0, and which is x is equal to x0 and y equal to y0. That is the initial curve we have given, where this x0, y0, z0 are continuously second order derivatives are there. Then what we are finding? We are finding the initial strip. Suppose that this P0 and Q0 are determined by these two equations that we were doing to find out the initial strip. And then we are saying that using that initial strip, we'll have a solution. Okay, so using this condition, that is f of x0, y0, z0, p0, q0, and d of dx z0 upon ds is equal to p0 dx0 by ds plus q0 y0 by ds, where this p0 and q0 are continuously differentiable function, and then we are calculating this value of p0 and q0, and that will leads to the equation of initial strip. And that satisfies this equation. Then it says that in some neighborhood of each point, the initial curve, there exists one and only one solution of this one is possible. That means it says that it is not only exists the solution is there, it's also saying that that solution will be unique solution. So whatever the examples we are doing in the previous lecture, this is the theory for that, or based on that this will be a theorem. So let us try to prove this one. So what we are doing is, let us consider the system of characteristic polynomial or characteristic equation, and we know that the characteristic equation are dx by dt is equal to fp, dy by dt is equal to fq, dz by dt is equal to pfp plus qfq, dp by dt is equal to minus fx minus pfz, dq by dt is equal to minus fy minus qfz. These are the characteristic equation are given to us, and we are considering this as a characteristic equation. And why this is coming, that's also we have discussed in the previous lecture. With the initial condition, or I can say with the initial curve, that is x is equal to x0 of s, y equal to y0 of s, and z is equal to z0 of s, will gives me that p0 of s and q equal to q0 of s. At point t equal to 0. So at t equal to 0, all this initial strip we get. Now what we are doing is we need to solve this system of ordinary differential equation, and that solution is possible due to the existence and uniqueness theorem for initial value problem for ordinary differential equation. So I can say that by existence and uniqueness theorem for the initial value problem for system of ordinary differential equation, we can solve above ordinary differential equations as x is equal to x of st, y equal to y of st, z is equal to z of st, p equal to p of st, and q equal to q of st. So this is the solution of that equation, where this x, y, z, capital P and Q have continuous derivatives with respect to S and T, and they are satisfies the initial condition, and they satisfies the initial condition x of s0 is equal to x0 of s, y of ys0 is equal to y0 of s, z of s0 is equal to z0 of s, p of s0 is equal to p0 of s, and q of s0 will be q0 of s. And that completes the proof of this theorem. Actually, the statement is much bigger than the proof, that I can say from this. That is, it's just we have used the one very important results is the existence and the uniqueness theorem for initial value problem for system of ordinary differential equation. By using that, you can say that the solution of this 5 equations are there and it is unique. Now the next proposition that we'll have, so proposition is saying that the characteristic curve x is equal to x of t, capital X of st, y equal to y of st, z is equal to z of st. Indeed, from an integral surface, so the characteristic curves indeed from an integral surface. This characteristic curves form integral. So what we are doing in the theory, sorry, in the examples, once we got the solution in terms of this form, that is x is equal to st, yt and zt, that we got the solution, we're trying to convert everything in terms of x and y and z. So this proposition is gives you guarantee that we able to always write down the integral surface in terms of x, y, and z by eliminating s and t from. So that is if s and t are solved in terms of x and y from the first two equation, then the last equation gives the solution expression in the form z is equal to z of s of xy and t of xy. That exactly we are doing. We are calculating what will be the value of s and t from this equation, and then we'll substitute that value of s and t into the equation of z. So the solution is always of this form. That means z is equal to z of xy. This we got always. Now let this x0, y0 be a point on the initial curve. Since the Jacobian that is a gradient, sorry, del of xy with respect to st at t equal to 0 will be f q dx0 by ds minus d, sorry, f t dy0 by ds is non-zero. This is actually given situation. You see that here. This is a gradient. And why it is equal to this one? The Jacobian that we have, this Jacobian we can know it is written as Sx St Ys Yt at t equal to 0. But you can just see that what is xs? It is dx0 by ds. So if I expand this one, it will give me sxyt minus ysxt at t equal to 0. What is sx at t equal to 0? We'll have it as d of x0 by ds. And what is yt? We already have this integral, that system of ordinary difference equation. Yt means dy by dt. It is fq. So that's why it is fq here. So that is fq minus ys, that is dy0 by ds, and xt, that is dx by dt, that we have fp. So that's why it is fq dx0 by ds minus fp dy0 by ds, and so that is these two quantities are equal. And this is true at every point. So this Jacobian is at every point on that initial line, on the initial curve. There exists a neighborhood n x0 y0. So the neighborhood of this point x0 y0. So that is very important result is there, such that this Jacobian gradient of this del of xy upon del of st is non-zero. So this is very important results that we have actually used here, that there is some function which is non-zero at x0, then there exists a neighborhood of x0 such that in that neighborhood, that is set of in that neighborhood, the function is non-zero for every x is in that neighborhood of x0. So this is very elementary results which might be you have studied in your complex analysis course, that if the function is given, and it is very easy to see for the real number. For example, function is 0, that means the function is above this x-axis, the function is here. Since the function value at point x0 is here, that is f of x0, then and the function is continuous function, then this the graph of the function is might be this one or might be this one, but it's never touch in some neighborhood you will always find, so that it will be non-zero. So exactly the same application of that result is here is used. That means if some function is non-zero at some particular point, then you can find a neighborhood of that point in which this function, this Jacobian, is non-zero. So in this neighborhood, n of x0 y0, we have the following well-defined function. That is s is equal to s of xy, t equal to t of xy, small x is equal to capital X of s of xy, t of xy, small y is equal to capital Y of s of xy, t of xy, z is equal to z of s of xy, t of xy, that is equal to z of xy. Then we have p, that is capital P of s of xy, t of xy, which is a function of p and x and y. So, and then last one is a q equal to q of s of xy and t of xy, which is q is a function of xy. We will show that f of f, this function f, will satisfy our original equation. So we will show that g of xy satisfies f of xyz of xy, zx, that is the value of p, and zy, it is the value of q, equal to 0. So this will be this equation will satisfy. That means whatever the solution, whatever the surface we get from this one, It is the solution of given nonlinear partial differential equation. So it is sufficient to show that P equal to Zx and Q equal to Zy. If we can show that this one, because of since f of xyz pq equal to 0, as the characteristic strip are essential, actually a solution of the equation, that is solution of this equations dx by dt equal to fp dy by dt equal to fq dz by dt equal to pfp plus qfq d p by dt is equal to minus fx minus pfz and dq by dt equal to minus fy minus pfz. Since it is the solution of this one, it is sufficient to show that p equal to zx. Let us consider u of st is equal to z s minus pxs minus qys. So let will be consider this. At t equal to 0, what will be this? It is u of s0. That is the value of this one at 0 will gives me dx0 by ds minus p0 d capital the small x0 by ds minus q0 dy0 by ds. And you should note that using that situation, that is this equation, that is dx by ds minus p0 dx0 by ds, and that equation leads to the situation that this quantity is equal to 0 by a strip condition, by the strip condition for initial element. This will be 0. Now our objective is to show that this u is 0 for all t. We shall show that u is equal to 0 for all t. So for that, let us see, consider. So ultimately what will show it is u is a constant function. So for that I need to show that its derivative is 0. So du by dt, the function u is this z s minus p x s minus q y s. So if I differentiate this with respect to t, so it is not d, it is actually del. So we have del u by del t is equal to zxt. It has to be capital zxt. Capital zxt, because a derivative of s is already there. So it is del st minus, here we have to use the product rule. The derivative of p, it is pt. Then xs is as it is, minus p as it is, derivative of sx is sst. Then minus, you have two function here is also qys. So the derivative of q with respect to t will give you qt, ys minus q yst. So combining these three terms, that is this one, and this one, will write it is del by del s of zt minus p xt minus q yt. So what I have done, so this term is as it is, the first one. Here you just observe that this four terms is already there. See, the first term is as it is, that is del by del s of this. Here I have subtracted two terms. That means the derivative of p into xt with respect to s will gives me ps xt. Here I have subtracted, so that means I need to add plus px st. But pxt is already there, so that will get cancelled out. No problem, we'll do that one. And here also this term is added, so del by del s of this quantity, that means q as it is, so that is q y st minus, this is actually plus q s yt. I just observe that this pxt and this quantity will get cancelled out. So finally what we get, it is del u by del t, it is del by del s of zt minus pxt minus qyt will have this two terms, so which is of minus sign, and plus these two terms. So we'll have minus pt xs minus qtys plus psxt plus qsyt. Now what will be this term? That is zt minus pxt qyt. That quantity is 0. And this psxt, xt is dx by dt, and the value of dx by dt we know it is from this sixth equation, dx by dt is fp, so that's why it is fp. So this value is fp ps, this value is fq qs, Now fx pt, that is dp by dt, but dp by dt is, you know, it is dp by dt is fx minus p fz, and this is of minus sign. So that minus minus become plus 1. We'll have fx plus fzp into xs. That is this term. For this one, it is plus fy plus fzq into ys. This we have used the initial strip. Now we'll multiply. So we'll have fx into xs plus fy into ys, that is this into this, plus fz into, you will have two terms. Fz will have this fz into pfx plus q ys. This is fz. Then plus this fp ps plus q into qs. Now here we'll adjust some quantity. That means we get del u by del t is equal to fx xs plus fy ys plus fp ps plus fq qs. So I have added these two terms. So that two terms will subtract here also, and all other terms will be there. So plus this term is there. So that term is fp ps is already there. This fpps is already there. fpps. So I've just written this term, this term, this term, and this term. And this term is why it is minus so that terms is there, and is minus fz zs minus pxs minus qys psx minus qys. psx minus qys minus fz into, now this zx is not there. Now what will be this quantity? That is Fs minus Fz, and this quantity is U. That we can see, we have defined U as this. Now that is equal to minus Fz U, because the F is 0 for every S and T. So this value is 0. And why it is Fs? It is nothing but the del F by del S. And F is a function of X, Y, Z, and T. So that term is also there, plus Fz Zs. That I have added and subtracted that this term. Okay. So this F is a function of X, Y, Z, P, and Q. So the derivative of F with respect to S will gives me this del F by del X into del X by del S plus del F by del Y into del Y by del S, and so on. So that is the thing we have here. And so we have this. Therefore, for fixed X, that means along the characteristic curve, U satisfies the following ordinary differential equation, that is du by dt equal to minus fz u, and we can integrate this, or we can have a solution which has a solution as du by u is equal to minus fz dt. So you will have therefore ln of u equal to integration of minus fz dt plus some constant ln of c. So finally you will have, it is u equal to c into exponential of minus of integration from 0 to t f of t dt, f of z dt. But this value of c is nothing but the whatever the initial value at z. So therefore at initially at t equal to 0, we get c will be u of 0. So therefore we have u equal to u of 0 into exponential of minus of 0 to t fz dt. Now we use the condition that u equal to 0 at t equal to 0, that we got. At t equal to 0, u is 0. So if we use that condition here, using condition that u is equal to 0 for t equal to 0, this above expression, that means this expression is leads to u equal to 0. We get, because this is u of 0, u of 0 is 0 as per this. So this u is 0 we get for all t. For all value of t, you have 0. And the value of u we can have obtained it, that is this zx. So this is equal to 0. Since this is equal to 0, we will have zs is equal to pxs minus qys. So therefore we have zs equal to pxs plus qys. And consider in that way a 4 equation. So consider the 4 equation. The first one is this, zs is equal to pxs plus qys. Second one is zt equal to pxt plus qyt. Third equation, zs is equal to zx capital XS plus ZY capital YS, and fourth equation is ZT equal to ZX XT plus ZY YT. So you consider this four equation. We already proved this. It has been proven. We already proved this. As you can see that this equation we have proved. The second equation, it is the characteristic equation. The second equation is the characteristic equation. That is dz by dt is equal to p dx by dt plus q dy by dt. So this is a characteristic equation. So it is a characteristic equation. The equation 3 and 4 are obtained by differentiating identity of equation. This can be obtained by z is a function of st and s and t are the function of xy. So sorry, the situation is, so now question how to obtain the 3 and 4. So what is the situation here? Z is a function of x and y, and x and y are the function of s and t. So the derivative of z with respect to s will give me zs is equal to del z by del x into del x by del s plus del z by del y into del y by del s. So it is exactly the same thing which we have written here. Del z by del x, that is zx. Del z by del x by del s is xs. And with respect to t, we also have the same thing. So this four equations, so this can be get from this situation. Z is a function of xy, where x and y are the function of t. So from this we can have this. Now we observe that this p and q are satisfies the equation 1, that means this equation and this equation. And zx and zy are satisfying the equation number 3 and 4. And you can see in this in a different manner, this equation 1 2 is same as equation number 3 4. So if that means the coefficient will be the same, and the determination of this coefficient is a linear system of is there, so that determinant will be non-zero, and hence we can have the solution, that is zx is equal to p and zy is equal to q, that we got. So that we should write here. Now we observe that this PQ satisfies the equation 1 and 2, and Zx and Zy satisfies 3 and 4. So here I have written 1 2, 1 and 2, 3 and 4. As a system of simultaneous equation, one and 2 are same as 3 and 4. Further, the determinant of the coefficient of this linear equation or system, this linear system, that is del x by del xy by del st, this has to be non-zero in the neighborhood of x0 or neighborhood n of x0 y0. Hence we have p of xt, it is zx of x of st, y of st, and q of st will have, it is zy of, this is zx, x of xt and y of st. Or I can say px is zx and py is zy. Or so therefore p of xy will be zx of xy and q of xy is zx of xy. And this we need to prove, and we have achieved that. Also, there is one thing is left to prove, that whatever the z we determine using this manner, it is unique. And that is very straightforward, that z of equal to z of xy, so determined, is unique. That means there is a unique solution is there. Previously we have talked about the existence of the solution. Here we are talking about the uniqueness of the solution. Suppose there will be two solution is there. Solution. Suppose that z1 z is equal to z1 of xy and z2 equal, z equal to z2 of xy are two solutions containing initial strip. Consider the any point on this initial data curve, and this two surface contains the initial element at that point, and the characteristic strip issuing from this initial element through that point, and therefore the corresponding characteristic curves lies on the both the surface. And as this has happened for every point of the initial data curve, this surface are generated by same characteristic curve, and therefore they must coincide, and thus the solution is unique. So suppose there will be two solution is there, and using that initial strip, I will pick any point on this initial data curve, then whatever the characteristic strip form from the initial element through that point will corresponding a characteristic curve that has to be lies on the both the surface, and this has happened for each and every point on that initial strip. So that means whatever the surfaces are generated, they are coincide. That means the solution is unique. And that completes the case that in that situation, that is Cauchy problem for nonlinear first order partial differential equations is exist and it is unique. We have solved many examples in my previous lecture. So if you have any doubts with this,